So what I wanted to do for this class is to go over a couple of physical situations where this concept of fermions is important, right? Where this really has a big effect on the physical properties that people care about, right? So let me first talk about atomic physics. That's probably the situation where it comes up the most. And this really, makes a connection with what you might have learned about in chemistry classes. Okay. So the idea of atomic physics is like this, right? So we talked about the hydrogen atom earlier in this semester. And so for the hydrogen, right, we have a nucleus with just one proton. And there is one electron that's moving around it. Right? And we worked out the solution for the wave function of the electron. That is, we treated the proton as if it's infinitely massive, as if it's a very a fixed potential. Okay, and so we solved for the electron wave function. So now the question is, how could we apply that to some multi-electron atom? Okay, so that would be a situation where we have a nucleus with a charge of plus ZE, where Z is the atomic number. That is the number of protons in the nucleus and also the number of electrons. Okay? And so then there are Z electrons that are flying around the nucleus. So ideally speaking, what we would want to do would be to solve for the wave function for all Z electrons. So that would be some psi in terms of R1, M1, R2, and M2, right, up through RZ and MZ, right, for all of the electrons that are going around the nucleus, with the idea that these are indistinguishable particles, right, which are all fermions. This is a hard job. Okay, this is a very hard job. And the difficulty is the electron interaction. Let's say the interactions among electrons. Okay. So, if we wanted to figure out what's the potential energy here as a function of all of the electron positions, okay, part of the potential energy is the interaction of the electrons with the nucleus, and then part is the interaction of one electron with another. Okay? And so for the interaction of the electrons with the nucleus, that would be minus Z E squared over 4 pi epsilon naught for magnitude of R1. Okay, this is electron 1 interacting with the nucleus. Okay, and it has this form because we could say that the nucleus charge is Z E, and the electron charge is, the electron charge is negative E. Okay, so this is the product of the charges in the numerator, and then divided by the magnitude of the distance between the electron and the nucleus at the origin. Okay? And then ZE times negative E 4 pi epsilon naught magnitude of R2, right, up to ZE times negative E over 4 pi epsilon naught R sub Z, right? This stuff is all electrons individually interacting with the nucleus, right? Then we have the electrons interacting with each other. Okay? So that makes, an interaction that looks like negative E squared 4 pi epsilon naught R1 minus R2 absolute value plus negative E squared 4 pi epsilon naught R1 minus R3 absolute value, etc., right, for all the pairs of electrons that might be interacting with each other, right? So here we would say the first set of terms, this stuff is not too bad, right? This stuff looks like it's each individual electron interacting with a potential, okay? So this looks like V of R1 plus V of R2 plus through V of RZ. That's not bad. But the line on the bottom, this stuff, this has all of the complicated interaction of one electron with another electron, and we can't assume that either of them is fixed. Okay? So this stuff is what is not exactly solvable. Okay, so in this situation, the problem cannot be solved exactly for more than one electron, right? For Z greater than 1, right? It can be solved exactly for hydrogen, but not for any of the other atoms with more than one electron. Right? But still, people want to know the answer, right? People want to be able to describe other kinds of atoms besides hydrogen. And so for that reason, there are various approximation schemes. Right? There are lots of ways to say, even if we can't solve things, exactly what sort of approximations can we make, right? And the simplest approximation is just to neglect all the hard stuff, neglect all the terms in blue. So to neglect the electron interactions, and to consider only the exactly solvable stuff. So consider only the interactions between the electrons and the nucleus. So this is a very drastic approximation, right? I mean, when you have a whole bunch of electrons moving around and they have some Coulomb repulsion from each other, it seems amazing that we could be able to just neglect that Coulomb repulsion. But you can get some level of solution this way. Okay, we'll say it is amazing that this approximation works at all. But it sort of does. Okay, so how does it work, right? So the way you do this, right, is to say each electron feels the same potential. Okay, which is the thing that I circled in red over here. So the potential energy V of R, which is the ZE times negative E over 4 pi epsilon naught magnitude of R. Okay. So this is the hydrogenic atom. This is just like what you had on the homework, not the most recent one, but the one before that, right? The homework where you had questions about solving Schrodinger's equation and this sort of potential, okay? And so you know the answers for this, okay? And so you know that there are eigenvalues and eigenstates, okay? So there are the hydrogenic energy eigenvalues, which depend on a quantum number n, right? So there's the energy eigenvalue E sub n. And what corresponds to those eigenvalues are eigenstates. And eigenstates, which in this case we could call wave functions, or we could call orbitals. Okay. And they are functions psi NLM, which depend on the R vector. Or we could say psi NLM, which depends on the distance from the origin and the angles theta and phi, okay, all associated with a particular electron. So this is the position in spherical coordinates. Okay, and in this numbering scheme, we have n is an integer from 1 to infinity, and L is an integer from 0 to n minus 1. and m is an integer from minus L to L. And the ENs, the energy eigenvalues up there, I guess I should write that out too. So En is negative, and we have this combination that you remember. Mass of electron over 2 h bar squared, z e squared over 4 pi epsilon naught, all squared, times 1 over n squared. Okay, so this is, a reminder of the solution of the problem for any single electron. Okay. So what's the ground state? For the ground state, that is the lowest energy state. Okay, so that means the energy is E1, and the wave function is psi 100 of r theta and phi. Okay, and you notice that this is not 100. This is 1, 0, 0, and I'm just leaving off the commas the way that people do. But that means that n equals 1, L equals 0, and m equals 0. Okay. So this is the ground state for a single electron. Okay. So now the question is, suppose that there is more than one electron. Can all the electrons go into that state? If so, then we'd have a pretty simple solution, right? All the electrons would be in that state, and the total energy would be the number of electrons, Z, times this energy, E1. But that doesn't work. No, the electrons cannot all go into that state because electrons are fermions. Okay. So because electrons are fermions, we have the Pauli exclusion principle. So these distinct but indistinguishable fermions cannot all be in that wave function, okay? Or because of the symmetry requirement for fermions, the anti-symmetry requirement for fermions. So what can you do? Okay, well, if there's only one electron, what is its wave function? Okay. Well, it needs a wave function that depends on the position of the electron and on the spin state. Okay? So that could be this psi 1, 0, 0. That's a function of r, theta, and phi. Okay, that's how it depends on the vector r, right, on the position, and then it has a spin state, which might be up, or it might be psi 1, 0, 0 of r, theta, and phi times the spin state down. It could be either of those possibilities, okay? And either one has the energy of E sub 1. Right? What if we have 2 electrons? In that case, we need a wave function that depends on R1 and the spin state 1, and on R2 and the spin state 2. Okay, and it has to be anti-symmetric if you exchange the positions and the spins. There are lots of ways to do that, but the lowest energy way to do it is if the positions are both in the state 1, 0, 0. So that's as a function of R1, theta 1, phi 1, and state 1, 0, 0 as a function of R2, theta 2, phi 2, times the combined spin state, which is up, down, minus down, up, over root 2. Okay, so if you look at this, okay, you can say this is the position state, and it is symmetric under exchange. Of positions, right? That is, if we just exchange the positions and we keep the spins the same, we don't exchange the spins, then the wave function stays the same. Okay? Now, over here, this is the spin state, and it is anti-symmetric under exchange of spins. Okay, so that means if you exchange, which is the spin of number 1 and which is the spin of number 2, then instead of up, down, minus down, up, you get down, up, minus up, down. So that's the negative of what you had before. Okay? So the product of those two things, the product of these is anti-symmetric under exchange of positions and spins. So if you totally swap, which you call electron number 1, and which you call electron number 2. You swap the positions and the spins, okay? Then you take the wave function and you multiply it by a factor of 1 times -1, which means -1, okay? So the whole wave function gets multiplied by a factor of -1 under that exchange. And that's good for fermions, right? That's what fermions require. So this is a good wave function for fermions. And so here the energy is 2 times E sub 1, right? Here it's energy is E sub 1. Okay, so the energy is associated with the position state, right? The energy is associated with the n quantum number, and the n quantum number is 1 for both of the electrons. And so you get a total energy of 2 E sub 1. Loosely, one approximate way to speak about this is we can say 2 electrons go into the state 1, 0, 0. 1 up and 1 down. Okay, and so you could say there's room in that state 1, 0, 0 for 2 electrons. One of them spin up, one of them spin down. That's allowed by the Pauli exclusion principle. Okay? That's a loose way of speaking, which is probably the way you learned it in introductory chemistry classes. Okay, and it's true. It does match what we have in this wave function. I say it's loose because it's not as if there's one of the electrons, that's the spin up guy, and another electron is the spin down guy, right? Really, there's an antisymmetric state that's involves both electrons, an antisymmetric spin state, right? Which is this combination of up, down, and down, up, right? And so this combination is neutral about which electron is spin up and which electron is spin down. And that's the way it has to be for indistinguishable particles. Okay, so that's how it is with 2 electrons. All right, what about with 3 electrons? Okay. So for 3 electrons, it is no longer possible to put all the electrons into n equals 1 states. We must go to a higher value of n. Okay, there cannot be a combination which is just in n equals 1. Okay. And that's because you can't make an antisymmetric spin state, right? Where all the electrons have the same position state. Okay. So you need to go to higher n. So you must go to a higher energy. That is, you can have 2 electrons in this n equals 1 state, and 1 in the n equals 2 state, which is higher. Okay, so that's for 3 electrons or 4 electrons. Okay, and then we can ask how many electrons can have n equals 2. Well, here we need to count the allowed values of L and M. Okay? So if n equals 2, then the quantum number L can be L equals 0 or L equals 1. If L equals 0, we have to have M equals 0. So there can be a state 2, 0, 0, right? This 2, 0, 0. And you can have 2 electrons in that position state because they can have opposite spin states. Okay? So that makes 2 electrons. And then when L equals 1, you can have M equals -1, 0, or 1. And with each of those sets of NLM, you can have 2 electrons. So this makes a total of 6 electrons. So adding those, it's N, it's 8 electrons, okay? So 8 electrons can be associated with the quantum number n equals 2. Okay. What about other values of n? Okay, well, for a general n, we could say how many states are there, right? Well, for L equals 0, there's 1 state, plus 3 for L equals 1, plus 5 for L equals 2, plus ... right, going up to n-1. And then times 2 because of the spin, right? 2 for the spin because there are room for 2 spins associated with each set of N, L, and M. So if you add up this series, that's equal to 2n squared. Okay, so we expect 2n squared electrons for each n value. And the word that people use for this is to call it a shell. Each n value is a shell which can hold 2n squared electrons. So the first 2 electrons go into n equals 1. Then the next 8 electrons go into n equals 2, and so on to higher values. Okay, we gradually keep filling up more and more shells, and we get a table. We get the periodic table. Okay, so let's see how many elements we would expect in each row. Okay, so we expect a periodic table. Okay, so for the first row, we should get 2 elements, right? We could get hydrogen and helium, right? Elements with 1 electron per atom or 2 electrons per atom, okay? And then for the second row, we would expect the elements where we're filling up the n equals 2, right? So 2 times 2 squared, so 8 elements. And here, let's keep going with what the prediction is from this simple kind of theory, okay? So for the third row, it would be 2 times 3 squared. That's 18 elements. The fourth would be 2 times 4 squared. That's 32 elements. And the fifth would be 2 times 5 squared. That's 50 elements. Okay, so then this is something that we can compare with actual chemistry, okay, to see how many elements go into the rows, okay? And so for the real experiments, in, what all of chemistry does, okay, they find the real periodic table does have 2 in the first row, and then it really does have 8 in the second row. After that, it's not a perfect agreement anymore, okay? Because then there's another row with 8, and then there's 18 in this row, and then there's 18 in the fifth row. So theory sort of partly works. It doesn't completely work, okay? So we could say, is this good news or bad news? Well, in the first place, it just depends on your standards, right? I mean, if it were me, if I could predict the first 2 rows of the periodic table, I don't know, I'd be pretty happy. I'd retire on that and I'd feel good about myself. But other people have higher standards than that. And other people would like to predict all the rows, not just the first 2, okay? And so something has gone wrong here, okay? So we'll say it's not bad, but not perfect. And the problem is what we've been leaving out, right? The problem is electron-electron interactions. Right? That it was always a very drastic approximation to be leaving out electron-electron interactions from this theory. And it's amazing that it works at all, but it certainly doesn't work perfectly. And here we're seeing the limitations of that. Okay? And one way to express the problem is that the energy really depends on L as well as M. In the hydrogenic atom calculation, the energy comes out to depend only on N, not on L. But that's not exactly true, right? That there is this degeneracy, right? That all the states with a certain value of N have the same energy, and it's not strictly true when we start including all these other interactions. Okay? And so there's a dependence on L. So for example, if we have n equals 4, L equals 0, this whole thing is actually lower than n equals 3, L equals 2. And so it is not true that you just fill up states starting with the lowest value of n and go up to higher values of n. You need to consider the L number also. And sometimes you start putting things into a state like this one before you do a state like that one, not after, the way you would think based on the hydrogenic thing. So that's a limitation of this calculation, okay? And so people get around it in different ways, okay? So one way to get around it is with sort of empirical rules. And so in chemistry classes, you might have learned rules that tell you which states get filled up first. And so there are rules that say, oh, well, you fill up based on N, except when you don't, and then you fill up based on L, right? And so there are rules that people have just developed over the years for that. Or alternatively, there are complex calculations, right? There are calculations where people put a lot of electrons into some computer, and so they go to solve the differential equations computationally with the correct potential energies, and that's a big job. But people do it, and they can discover a lot about orbitals that way, and what are the energies associated with orbitals, right? So it is sort of beyond the scope of this course to go into how to do those calculations. That's way beyond the scope of this course. But here you can at least see what are the differential equations that people want to solve. So this whole thing, well, I guess one other thing I'll mention to you, as long as I'm showing you this, there's a weird notation for orbitals that I just want to show you because you might come across it in some places. There is a notation to describe all these possible states, okay? And that is to use a certain letter for each value of L, okay? So you remember there's the quantum number L, which is associated with the orbital angular momentum. That is the angular momentum operator, the L squared operator, capital L squared operator, has an eigenvalue that is little l times little l plus 1 times h bar squared. Okay, so there are states with different values of this orbital angular momentum quantum number, and each of those things is conventionally given a letter. So L equals 0 is called S. L equals 1 is called P. L equals 2 is called D. L equals 3 is called F. Okay, why these letters, you are wondering? Well, this is really old-fashioned notation, and when people were first observing spectral lines, right, doing spectroscopy experiments, even before they really knew much about quantum mechanics, so they didn't really know about angular momentum. They just described these lines empirically. And they said some of them are sharp, so we'll call them the S lines. And some of them look like the most noticeable ones. We'll call them the P for principal lines. And D is for diffuse. And F is for fundamental. I don't know how they really came up with these letters, but these names have stuck, okay? And so you often will hear people talk about S electrons or P or D electrons, and this is what it means, right? It all has to do with this angular momentum quantum number, okay? And so in atomic physics, people can describe an orbital by the n number followed by the L letter. So you could describe an orbital as 1s or 2s or 2p or so forth, okay? And that means n equals 1, L equals 0, n equals 2, L equals 0, n equals 2, L equals 1, and so forth. Right? And then a superscript for how many electrons are in that orbital. So in that N and L, okay? So for example, in the ground state of carbon, so that is atomic number 6, right? Z equals 6. So people could write that as 1s2, then 2s2, and 2p2. Okay, so that makes 2 plus 2 plus 2 electrons, so 6 electrons. Okay, so that's a notation that you might have seen in chemistry classes, and physicists use it too, to talk about, you know, S or P or D electrons, depending on the orbital quantum number, the orbital angular momentum quantum number. Okay, so this now is kind of a prequel to chemistry, right? You know this word prequel, like for Hollywood movies, right? Like Star Wars Episode 1 came out after the other Star Wars movies, but it logically goes at the beginning of the sequence, right? I still think of that as one of the new Star Wars movies, but it was probably before you guys were born, right? All right, so anyway, this is like the prequel to chemistry, right? So this is what logically comes before the chemistry that you might have learned in freshman year, but you are learning it now years later, right? After you've had more math preparation. All right, so that is what I wanted to tell you about atomic physics. And especially because I want to connect what you've been learning about through this quantum mechanics course with what you've seen in other contexts in chemistry. I have one other story prepared here about why fermions are important. And here, let me do that. I can do that in 25 minutes or something. Okay, let's talk about another story. Okay. And my second story about the importance of fermions is in the context of magnetism. So earlier when we were talking about magnetism, I was saying, what if you have an applied magnetic field? How does that affect a single electron? Okay, but now let's suppose you have a crystal. And a crystal is a whole lattice of atoms. And so, we might draw it with a picture like this. Okay, so here's a square lattice, for example. Okay. And on each lattice, on each lattice site, there's an atom, and each atom has electrons. And the electrons have some spin. Okay? And so associated with the electrons at each site, I could say there's some spin. So spin S of electrons at each site. And then, as we discussed previously, when there's a spin, there's some magnetic dipole moment. Call it mu. Okay, so everywhere here, there's going to be a spin. Okay, so I'll draw some spin arrows, right, to represent which way it goes. Okay, and then there's a larger scale physical question. Okay, that is, what's the statistical ordering of all the spins? Okay, do the spins tend to align with each other, or are they all random? So is it a case of random spin directions, or is there some case where the spins align? If the spins align, we call that a ferromagnetic phase. And here, the prefix ferro, you can recognize that sounds like iron, right? So this is what iron does when you get a magnetic piece of iron, right? That the spins are aligning in some direction. So this really can happen in materials like iron. You really can get spins aligning with each other. And so it is making a state with some magnetic order like that, where the spins are picking a direction and lining up in that direction. Okay, so then the question would be, why do the spins align? There must be some kind of energy that favors aligned spins compared to non-aligned spins. Okay? Now, the first thing that you might guess as an energy to explain this kind of alignment is the magnetic dipole-dipole interaction. Okay? So that's something that you presumably learned about in an E&M class. Okay? So in an E&M class, you would have seen that if you have two magnetic dipoles, as with two electric dipoles, there's an energy of interaction which depends on the relative orientations of the two dipoles. Okay, and the equation that you might have learned for that looks like this here. It depends on the distance between the dipoles with this 1 over r cubed. And then it involves 3 mu1, so the dipole moment of dipole 1, dotted into r hat, where r hat is the unit vector between the dipoles. And then mu2 dot r minus mu1 dot mu2. Okay, so the picture that goes along with this is that you have 2 dipoles like this, mu1, mu2, and they are separated by some r vector. Okay. And the interaction energy depends on each of these vectors, the dipole vector, but it also depends on the vector between them. And so partly it depends on the vector between them through this 1 over r cubed dependence, but also the interaction depends on the relative orientations of all 3 of these things, mu1 and r and mu2. Okay, and so you would get a low energy if the dipoles are parallel to each other, one on top of each other. And you also get a low energy if they are anti-parallel to each other side by side, like that. So it's not the case that this dipole-dipole interaction favors parallel or it favors anti-parallel. It favors both of those things depending on the relative positions of the dipoles. Okay, so then the question is, can this dipole-dipole interaction explain ferromagnetism? Right? Can you say this is the fundamental mechanism that makes all the magnetic spins in a crystal line up with each other? It seems reasonable, but it's not correct. Okay, there are 2 problems with that explanation. Okay, so problem number 1 is that it favors different alignments depending on the relative positions. So that's, for the picture that I just drew for you, right? That if you look at sites like, here, here to here in the lattice, the dipole-dipole interaction favors parallel. But if you have sites like there to there in the lattice, the dipole-dipole interaction favors anti-parallel. And so, it doesn't make a single story about which way they should align. And the other problem with this as a potential explanation is that it isn't strong enough. And so for people who've estimated what's the magnitude of this dipole-dipole interaction, it's way too weak to account for ferromagnetism. So instead, there is a more complicated story which involves the fermion nature of electrons. Okay, so let me try to say what this story is. Okay, if if you have neighboring electrons with the same spin, okay, so that would be a picture like this. Okay. Let's think about the symmetry of the wave function for the two electrons. Okay. If it's the same spin between them, then the wave function has to be symmetric under exchange of spins. But certainly if you exchange those two spins, it's the same state. Okay, so the wave function has to be symmetric under exchange of spins, but we know the wave function has to be anti-symmetric under exchange of spin and position. So it must be that the position part is anti-symmetric. Under exchange of position, okay, but we already saw in the last class a consequence of the anti-symmetry under exchange of position, right? Because it's anti-symmetric under exchange of position, the electrons must be farther apart. The electrons have to be farther apart, right? When you have the anti-symmetric position wave function, there is zero probability for the electrons to be in exactly the same place, and there's a reduced probability for the electrons to be close together. So the electrons tend to be farther apart, right? And we calculated one example of that, on Monday and Tuesday, right, where the positions are farther apart. And the electrons really do have some Coulomb repulsion, right? The electrons have the Coulomb repulsion between each other, which tends to favor pushing them farther apart. So the Coulomb repulsion is lower. Okay, this makes a potential energy which is low when the electrons have the same spin. Okay, by comparison, what happens if the electrons have opposite spin? I'll just write it in red on top of this. Okay, if the electrons have opposite spin, like this and this, okay, then the wave function, well, I won't say it has to be, but it can be anti-symmetric under exchange of spin. And for that reason, it can be symmetric under exchange of position. And so in that case, the electrons are closer together, and then the Coulomb repulsion is higher. Okay? So this makes a Coulomb effect, which favors same spin, and it disfavors opposite spin. So the Coulomb repulsion, the Coulomb interaction between electrons, then indirectly favors same spin. It's an indirect effect that comes because of the fermion character of the electrons, right? That the fermion character of electrons is making a relationship between the spin wave function and the position wave function, so that the Coulomb repulsion has this indirect effect. Okay, so this is a kind of exchange interaction between electrons. And it works no matter what the relative positions are. And so it favors same spin, whether they're like this or if they're side to side like that. So it solves that problem. And this is a strong effect. The Coulomb interaction between electrons is actually, when people have calculated it quantitatively, it's a very strong interaction. And even when it works through this indirect exchange mechanism, it still strongly favors the same spin. And so this does explain the effect of ferromagnetism. Yes, so this is another way in which the fermion character of electrons becomes very important. And I have 5 minutes left. I'll tell you one more mini story, okay? In 5 minutes, I'll tell you a mini story about neutron stars. Okay, so this is my mini version of what Professor Dexheimer works on. So don't tell her that I tried to say it in 5 minutes. Okay, so the idea is, not only are electrons fermions, but neutrons are also fermions. So neutrons have the same issue with the Pauli exclusion principle. Okay? So what happens if you have a whole bunch of electrons that make up a star? Okay, so you have a whole bunch of neutrons, right, making up a star. And where can you put them? Can you put them all on top of each other, right? So I'll say here's neutron, 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 right? Can they overlap each other? No, because of the Pauli exclusion principle. That prevents them from being right on top of each other, okay? So if you have a large number of neutrons that form a star, we can say there are two important things that determine how big will the star be. There is the Pauli exclusion principle that keeps the neutrons apart. And that is fighting against gravity, which pulls the neutrons together. So you get a competition between these two things, okay? And the competition between these things favors a certain radius for the neutron star. If you didn't have the Pauli exclusion principle, then the whole thing could just collapse, right? It would all just pull all the neutrons together right on top of each other, okay, in some minimal volume, okay? But the fermion characteristic of neutrons prevents that from happening. Right? And so the whole neutron star is sort of like particles in a box, right? But it's not a box; it's a sphere, right? It's neutrons in a sphere, right? And so there are many neutrons in a sphere, and so they have a certain set of allowed states, and they fill up those states, starting from the lowest energy ones and working their way up. So the same as electrons in an atom start with the lowest orbital and fill their way up. Here it's neutrons in a box, a star box, fill their way up. And that makes the properties of a neutron star. Okay, and so something like this would make the simplest possible model to determine what is the radius of the neutron star and what's the total energy of the neutron star, of all the neutrons packed together that way. That's like the mini version. And then, of course, Professor Dexheimer works on much more precise kinds of studies than that. Okay, so those are three kinds of little stories in an hour and a quarter about why fermion properties are important. Okay, and so especially for the atoms, that's in chapter 5 of the textbook. Okay, and so this wraps up what I wanted to say about quantum mechanics with more than one particle. And next week, I'm going to begin with the last topic about perturbation theory. And next week, I'll assign the last homework with a little bit of perturbation theory and a little bit about bosons and fermions then. Okay, so let's take a break here and have a good weekend. And I will see you guys on Monday. All right, so long.